whatever purposes, maybe I also screencast this. So that's my intention. Actually, I'm going to talk about. Last time we talked about feature edges, right? We talk about edges as features. So this time we will look into corners. Then maybe next time we will talk about sieve. So that's my. I'm thinking also for this one I may I still probably I still haven't made up my mind. So I want to. You guys for the third homework will be try to implement the Harris corner detector. It's not actually difficult, but it will be compared to the last two homeworks. It's more low level. But again, I will kind of show you the solution. So if you really get lost, yeah. But of course I won't post it. But yeah. But basically it's the same thing because I'm screencast this thing. So if you're really stuck, you can just take a look of that. So so basically I guess just some background why we want to look into. Last time we looked into edges, right? So as I mentioned, we were looking into corners, and next time we'll talk about some kind of these feature points. So corners, you can even think of corners already feature points, but there's some more developed feature points such as sieve, serve, all these other algorithms. But corners, you can think of as a foundation, starting point there. And we're interested in these feature points because I just think of if I want to recognize two things here. I want to recognize this stop sign. Some of the simplest way to do this recognition will be I just try to get some feature of this stop sign. I have registered this image, get some features here, and then here I try to look for exactly those features. And of course, for those features, I cannot extra features such as the wet background here. We cannot from there basically you cannot distinguish this point correspond to any points here. So because this, if you try to match, it can match to any points in this background here. Right? So we want to look for something is salient, distinguished. So for example, the T here, maybe the corner of this T here will be kind of at least human-wise, I can identify this point exactly to this point here. But there's no way if I say try to look for this point, the corresponding point here. Of course, I can approximately point it, but it's just based on the fact that I know the geometry and somehow that kind of stuff. But it's not, I really get the distinct feature from that point there. So, and if we get those points, we can do lots of stuff. For example, an example, we'll get into that in several weeks. For example, to estimate the cameras, some of these parameters of the camera, some of these so-called fundamental matrices, when you have two cameras, stereo field, and of course, structure in motion, structure for motion, stuff like that. And there's more example.
What is structure for motion?
Oh, okay. It's you kind of move cameras around, and then you just build a 3D structure from whatever video you capture.
But does this require known points?
No, that the technique would be very similar. This would be some of the some of the core element will require what we just mentioned here, the feature extraction, right? So if you have a video stream, continue to move the video stream, then you frame by frame, you try to find the corresponding point from one frame to another frame to the next frames. And then hopefully you have the correct matches there, and then you try to, from those matches, to get the orientation of that camera first. So you know the camera orientation, then maybe you can do the dense matching then. You have a good calibration there now. Then now you're starting to point by point try to look for correspondence. But typically it's harder. Then you need to make some assumption there. or like, for example, if you have like, I move the camera around.
Are all those black
Yeah.
points, like points where the camera was?
Oh yes, those are the camera walls.
Okay.
So here is a doing diff. You can have like several setup. For example, like this setup would be like you just have many screenshot, many photos, or you can just, as I mentioned, you can have video just moving around and then continue to. Yeah. But either way, we will need to try to get the feature points and do some matching there. So and so that's why feature extraction is useful. And there's some other. Actually, I think most useful is still like this kind of alignment, reconstruction, or maybe SLAM, like doing this robotic stuff. Recognition is no longer because you have deep learning is doing pretty well. So I guess you can still like try to build something based on this, especially if you have like restriction on the computation power that you have on your devices, maybe. Yeah, but anyway, so I guess we'll talk more about it. So we want to look for invariant feature, right? So maybe I just go all the way to corner detector. Let's see, parameter stitch. And that's another example again. I just actually last time I also make this one as a homework. Like you can try to find the corresponding points. Afterward, like let's say if I know like point by point here and there, so here. So then this would be a easier problem than what I just described, that structure for motion. Like this one, I just do a 2D stitching to make lines, as you know, like those already like those what's that? Application is already available in iPhone or something like Samsung, like whatever Android phones and so on. So you just move camera around and then you stitch all the picture together. So if you're interested, we can make this as a homework again. So, but yeah, we'll see about that. So of course, getting features, we want to make sure this is repeatable, salient, compact, efficient. So that basically we get the feature points. There's two things here. One is that we get the location of the feature points. We decide like which points is a good feature points. So we call those key points. Then afterward, we want to extract a feature there. So basically build a so-called descriptor. So hopefully if I build a descriptor of this point here, and if I have another view, a descriptor built on this point, like these two descriptors can match each other. So typically, for example, if I use sieve, the length of the descriptor will be like 128 elements. So it's a vector of like length 128, and you just compare these two vectors. If these two vectors match each other, then you say it's they match basically. You just basically match it in the vector space. So, but okay.
Are we gonna have a stitching assignment?
Yeah, we may. I'll see like if we're going to do that. Yeah. Do you want that, or like are you interested in that, or like or you think it's pretty
that's
painful?
obviously any of this stuff we could do on our own, but a little bit of guidance with something like that, I don't know.
Oh yeah. You will have lots of guidance, because last year I got lots of complaint from a couple of the assignment. So but honestly, I put up the video and even have the solution, but I guess I didn't advertise the solution is there. Oh, I don't know. So anyway, but so it should be enough guidance, and as I mentioned, the solution is likely to be there. But of course, I don't want you to just copy the solution, or like you at least you try to understand what's going on. Otherwise, it will be useless way. So so let's see. So And yeah, some other comments here, but maybe of course some of this is obvious. You want to like, you can extract the same set of feature points from these two views here. So it's not always obvious, like how we may be able to do it. Of course, like, if we can, then it won't be nice like as feature points, because like here, basically it's none of these can match with each other, because they are basically pointing to extracting different key points here. So like here, you have a key point here, but here does not have a corresponding key point here, so there's no way we can match it. So this repeatability is important, and hopefully like this detection, whether like we will catch the same point, will be kind of independent of your background or like your environment, like how you set up the camera and so on. And this is I may repeat a little bit to that next time when we talk about SIF, but I guess I just want to focus on the corner detector. So this is like the most obvious like features, right? You think of like, basically when I say corner detector will be maybe this point is like more or less like a corner. So or maybe I see yeah, maybe this is a better example. So if I have like I don't know what is this actually, like a rectangle here. It's a little bit smooth, but kind of we can consider this here is a corner, right? So if you think of like what's different of a corner from like an edge or a flat surface, flat region? Yeah. Yes, that's really nice one. That's exactly the idea, but we want to do it a little bit more efficient. For example, like what we can do is like the first algorithm we can think of is like we can take a patch here, then we move around, right? We compare the neighborhood of, for example, I just take this patch here, I compare with a patch I shifted like maybe 1 pixel or 2 pixel upward. Right? If it's a corner, that two patches won't match each other. But if I at this edge here, like if I compare this patch with a patch just move up by 2 pixels, they should match pretty well with each other. Does it make sense? So we can use that as a property. So what we want is like if we move the patches around, like left, right, up, down, and the resulting patch does not look like the original patch, then we can say that this is a corner. So this is the main idea. But you can see there's some nice math there. So that's why it probably like comparing last time, we spent a little bit more time on this. So the problem, as you can see, is like for stability, I need to compare like quite a lot of patches. For example, like I may compare like go up 10 pixel, go down 10 pixel, or even more, like maybe 20, 20, and then 20, 20. Then I will have like I compare 40 by 40 patches. So maybe like 40 times 40, like almost 2,000 pixel patches. So that is quite computationally intensive. If I just implement like this, it can be real time, or like it will become wasted, like loss of computation power. So, but that's basically the idea. So we'll construct a kind of a function like this. So, but the notation is honestly, you need to think of like this is just we are considering 1 pixel. So we are considering one particular pixel here. And we move. So for that pixel, we have a patch, right? So I add that. Let's see, what's right? X, Y. Yeah, I would say this notation is not precise, but that's what everyone uses. So, but as long as you understand the attribute what is referring to, that's fine. So you see like you are basically for, I have a filter here. So this W is like a window, like kind of like center at some, think of like a center at like just the origin, like 0, 0, or like some points here, I don't know, center here. So I have a window here, like the WXY here. So basically here, like it will be 1 and outside will be 0, right? So then I just basically have this IXY here, will be like points like everywhere, like it's the intensity of an image. So I shifted that points, like for example, I consider this point here. So if I shift, like let's say U is equal to 10, V equal to 0, then I basically shift horizontally, right? I shift here, so I consider a point here, and I try to look at the difference of this point compared to this point, right? And then, and I do that, like, so essentially I'm comparing like every point, every shifted point with the current point here, right? But I have a windows there. I just consider the neighborhood of this point here. So the windows is like center somewhere here, let's say. Of course, it's not specified here. There's no rotation specified here. So, so as I mentioned, this is like the windows, and so maybe just like to check your understanding. I'm not sure how easy you can say. There's like 3 courses here. There's like one here, and one here. So I'm computing this EUV. So as you can see, UV, as you change the, the degree of displacement, this U and V here, you can form a kind of itself from like an image here, right? So just from what we discussed here, so can you identify like which one is corresponding to which one here?
Is the darker one the one out there in the sky?
Yes. So this is a more like CO, so it's more flat. So EUV is kind of flat. So although it doesn't look like very flat, but yeah. So and so then.
I only see one other cross.
Yeah, that's one here. Like it's like.
Oh, okay.
Yeah, it's very hard to see.
Okay.
Yes. This is like more or less like the corner one. You shift a little bit, then like you doesn't match, right? So you shift a little bit, doesn't match. So therefore, this will be the edges basically. You can see like if you shift along this direction here, so you have low values. So but for the other direction is you have high values. Yes. Yeah. So as I mentioned, this is the idea, but it's not efficient. It's very slow to compute because you need to compute lots of patches there. And what we're interested in is, if you think of this, we just need to we don't need to compute this exact EUV here. Right? What we would want is just we want to get the shape, right? We want to know whether it's like this. Kind of like what's that? Like a cone going down, like a big hole going down, or like you have a kind of a channel, or what's that called? Like I don't know what's that called. Anyway, a trench, yeah, and or like it's something flat, right? So we don't exactly need to know like what's precisely this function EUV behave. I mean, not behave the exact values, but we just need to know like the shape of that. So therefore, like we may get away with that by simply try to do Taylor series expansion. So since I don't care the exact value, so maybe I try to do a Taylor series expansion of this guy here. with different UV. So I try to say expand this, approximate this as a Taylor series expansion. So just want to check you guys remember what's Taylor, or the Taylor series expansion is just you have, for example, if for a 1D function, so if you have 1D function here, so if I have fx here, let's say fx, so if I start at x here, like this point here, x, if I move a little bit this x plus delta x here, so I can approximate the value of this point fx plus delta x as fx plus kind of like this slope, right? I have the slope here multiplied by this with delta x here, right? So therefore it's plus the delta x multiplied by df dx there, right? df dx, or partial f partial x at this value here. Okay, I use the same x here. So anyway, right? So if you're 2D, basically, if I do I can do the same Taylor series expansion, but then I have like two direction here, right? I have going like the x direction, I'm going to the y direction, so therefore I will have something like that. And then so I substitute this one into here, so then I will just have this got cancelled, so I only have this here, and it's getting very ugly now. Let me just erase the so then for this one here, as you can see, like I can really write it in a matrix form, right? I mean, this guy here, just ix. Okay, this one here is just like ix u plus iy v, right? Okay, so anyway, so but then like this thing is itself a vector, so then this square here, I can write it as a transpose. This guy multiplied by the same thing transpose of this thing, right? So M transpose of this guy will get this one here, so I have this one here. And then so then let's see, here is sum over just xy, right? So I can pull uv out, pull outside, uv pull outside. I can just compute this first. So then this one is I can call it m or something. But as you can see, this one is, I'm essentially, what is this doing? It's just doing a filter. So because ix is like high pass filter, right, along like one direction and the other direction. So I basically just do a filter like in one direction for and take the square, and then like this one is basically to take one direction and the other direction, and afterward I just take a kind of a low pass, because this Windows is essentially a low pass, and I take a low pass of that thing here. And is that clear? So let's say I have this M and UV now. So just based on the M, I can know what kind of shape it is, right? So this basically captures all the characteristics of what we have that patch before. So what I mean, this M here, just looking at the M matrix there, we will know whether it's like this type, or this type. So essentially, you replace the patch by just a we just fit that by a second order kind of approximation, basically, and So here, just as I mentioned, like to find this Ix is just a high-pass filter. Right? So we just do what we had been doing like for the last several classes. So we just do a high-pass filter like in horizontally, vertically, and so on. So if like I have Ix, Iy, I just do horizontally and then vertically, or vice versa. Now from M, we need to determine whether what shape we have. So if you think of that, this is really a second order approximation, as I mentioned, and I can draw this level set here. It's called level set. I always don't know how to call this thing. So and this is basically a parabola like, and in 3D, how do you call that? Paraboloid or what? I don't know. Yeah. And so I can set this to constant, and then I will draw this level set here, basically. And think of this. Okay, then it's getting, yeah. Okay. Any question? This one is like found a little bit. So no. Just, please, you're helping me honestly. I have like trouble like expressing myself like. Typical question will help me a lot. Yeah. So.
I'm trying to remember the equation of an ellipse.
Okay. It doesn't. So okay. Think of this as like M is a matrix, right? So if I write it like, for example, A, B, C, D. Oh, by the way, this matrix is symmetric, as you can see earlier. This is A, B, C, C, I say. And then if I write UV here, I shouldn't use this. I hate this.
Oh yeah, I know what's happening.
Yeah. Then you see it's like really a. But let me. So A, B, C, C. Let's say. Oops. C, C, and UV. Have UV, or like you think of this as XY. Then you expand out will be like A U square, right? Plus B V square plus 2C UV, something like that. Yeah. So and this is exactly like a quadratic thing. And then like basically if you and when do you have this shape basically? What do you think? You can have different combination. This is like 2D. You have can have like different. This is like you can also go this way, right? But you can also go like some weird way. For example, like you can go like oh shit, I have no talent in drawing at all. Like this, like I don't know how to draw it. I don't know whether you get what I mean, like okay, in one direction it's going up, the other direction is just like not changing at all.
Okay.
Or you can have a even, I'm not sure. Oh no, that's not possible. Yeah, basically it's like this, I guess. Or fat, say. And now I can draw the level set way, as I mentioned. Now let me draw the level set like this. So let me call this a function of UV, right? Let me call FUV. And let's say FUV is equal to some constant here, maybe equal to C1. Now I have this UV acid here. Maybe I use a thinner pen, it's easier. So so maybe let me draw it more interesting. Let's see. This is like this FUV equal to C1. Let's say maybe I write it equal to 0.5. Let's say, and then I have this another one. FUV is equal to 1. Let's say. Okay. Let's say I have something like that. Maybe this is the level. FUV is equal to 2. My question, okay, couple question. This is nice, linear algebra. So, how do I know this direction here? You see, the direction I'm pointing is the direction is have like,
The gradient.
yeah, not changing that much. Actually, this is the small gradient because you see, it's like this one is not going that steep. This one is going steeper. This is the steeper gradient there. But how can I find these two S's here?
Divergence?
Huh? Right?
Isn't that divergence?
You mean the gradient? But actually from here I already have the gradient information here. You have the, yeah, you let's see. Let's see, if I take the gradient of that one to a u. Oh, but that, I only, okay. But you don't know where to take it. But for example, if I take the gradient, compute this center point here. So as you can see, what is the gradient there? Del f will be equal to 2au, right, plus 2cv. And here is like 2bv plus 2cu, right? And then like if I look at the center point, it's just 0, 0, right? So this is just 0, 0. It doesn't give me the direction there. But I should have this information from here, right? From this equation here, right? Because this abstract all the shape here. Or like simply from this M matrix here, I should have all the information, right?
We can try to find a distance between that origin point and the end of the vector, and if the distance to go between two contours is larger in one direction, then you have smaller gradient in that direction.
You right, but wait. Iswa, do you see that I just mentioned here? Like, so here, like for example, like at which point you should compute the gradient? Because like, for example, I cannot arbitrarily take a point here, right? So I may take a point like starting at the origin here,
Yeah.
but the origin is just 0, 0. If I compare gradient, that point is flat, right? Because I have a parabola, right?
So we can take the square root of like a squared plus b squared. Yes.
Do you remember something from linear algebra? That's the nice thing about linear algebra. Like, do you remember like some eigenvectors thing? He has a very nice interpretation here. It links up like linear algebra with this geometry. It's pretty neat. So you think of this as M here. So like, let's say I have the eigenvector. Remember, we say like eigenvector is basically like you have mv is equal to just lambda times v here. And for a symmetric matrix here, actually we can find the complete set of eigenvectors to form the basis. So I know I have like two eigenvectors here, like I have v1 and v2 here. And by the way, these eigenvectors will be orthogonal to each other. If my lambda 1 and lambda 2 is not equal to one another. So you can quickly show that because I can write like v1 transpose m v2. I look at this side here, I will have v1 transpose lambda 2 v2, right? But I can also look at this side here. This side is basically m v1 transpose, or like m transpose v1 transpose times v2. But m transpose, m is symmetric, right? So m transpose is just m itself. M v1 is like lambda 1 v1 transpose v2. So therefore we have like v1 transpose v2 times lambda 1 is equal to v1 transpose v2 plus lambda 2. So lambda 1 and lambda 2, if they are not the same, then we will have like v1 transpose times v2 is equal to 0. So, or maybe I just write it down. So lambda 1 minus lambda 2, so I get v1 transpose v2 is equal to 0. So therefore, if this is not the same, I have like v1 perpendicular to v2. And actually, I claim like these two is actually v1 and v2. So how can we see that? Like, so first of all, like let's make one more assumption here. This v1 and v2, I can normalize that, right? I can make it a unit eigenvector. So I can make it not just like they are orthogonal to each other. I can have v1 transpose v1 is equal to v2 transpose v2 is equal to 1. So you just normalize that. That's nothing special. And then let's see what then I can do. Then what can I do is I can make these two equations combine to one another. I need some space. Let me have an eraser to clean up some space here. So as I said, like these two equations I can combine with one another as m v1 v2 is equal to lambda 1 v1 lambda 2 v2. So here, like both of them is a column vector. Right? I just pat them each other. Right? So this is now a matrix 2 by 2 matrix now. And note that the trick, I guess you may have seen that before, is like v1 v2. I can write this as like this, lambda 1 lambda 2. Right? So then like what you see is like this, I can call this a V, or like something like a matrix V here, or maybe I call it U. Do I use U somewhere? Or O. Anyway, O stands for orthogonal. Then I basically have M times let's see what O inverse. Basically, both on the left hand side multiplied by O inverse. O is equal to lambda 1 lambda 2. So I can diagonalize that. Now let's see. Now I can put a okay. What I can do is I can put a actually I already done here. Okay, how should I write this? Now I can write like this. By the way, O inverse is actually just O transpose, because you can see that like O times O transpose times O is equal to V1 transpose V2 transpose V1 V2 here. I mean, because it's orthogonal, right? As I mentioned, like V1 transpose V1 orthonormal basically is 1, and V1 transpose V2 is 0, 0, 1 here. I have like this is a orthonormal matrix. And let's see. Now I can, as you can see, I have this one here. So actually, this should give me lambda 1 then. Oh, I need to look at the cheat sheet. What's the best way to explain this? Let's see. Where are we? We're quite far already. Yeah, okay. So, okay, I use R there. R is my O now. And yes, yeah, that's what we have here. Like M, we have DUV is equal to this guy. Then like I said like M, I can like decompose like using O. So O is my R. So then I can rewrite that earlier we have like O inverse MO is equal to this one. So therefore like O this one times O inverse equal to M. So I have this one here, that's fine. And then now you can, if I look at it, this is like this R or like O multiplied by this UV, you can think of this the new coordinate there. So then I essentially I kind of like after this is actually a change of the change of the axis here. I did a little bit rotation here, and after that, like when I change the variables, I essentially have a just have the off diagonal diagonal elements will be gone. It's just a linear equation like this, and so now you think of like at what time. So then this one is essentially is exactly the major and like minor axis there, right? If you think of that, like after this, for this case here, when I have this off diagonal line is like gone, this is like just a major and the major and like minor axis is just the x and y axis, right? That's basically we have like, oops, that's very painful. Well, I mean, like again, like this one is just lambda 1 u pi square plus lambda 2 u pi square. This is just a ellipse, like kind of like align well in the x and y axis, right? And now the lambda 1 and lambda 2 is basically the raise, or like you can think of like the inverse of lambda and lambda 2 should be the length of this guy here, right? Do you agree with that? Like, or like actually, I should be precise. Should be lambda 1 inverse square root will be the length of that. Because if I think of like the points here, for example, like point here, this is a lambda. This is basically lambda 1, right? So this point here will correspond to like v is equal to 0, right? V equal to 0, so this is like V here, V equal to 0, that is gone. So I will have like U pi square is equal to 1 over lambda 1 here, right? Or like this, I use lambda mean here. So therefore U pi is equal to 1 over lambda mean inverse here. Okay, so which did I make?
What?
Did I make F1 loss?
I don't know.
Did I make you loss?
Yeah, a little bit. That's
So
okay.
any question? Like no. So here, do you agree with that? Like so, this one is basically it's just lambda 1. Yeah, this is lambda 2. Yeah, if I look at it this way.
I mean, it's nothing we can't figure out.
Oh yeah. Okay. That's fine then. Yeah. So then like your rotation will be like this, right? Then the change is like this is essentially just rotating that, right? So that's basically the minor and major axis there. And but okay. I guess I dragged too long. But then this, as I said, like these two axes is the eigenvectors. Actually, that we don't care. Actually what we care is these eigenvalues, right? So basically the eigenvalues, what do we want the eigenvalues if it is like kind of like corner? Okay, at least this is relevant to us. If it's a corner, the eigenvalue is supposed to be what?
8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8. 8
if we want a corner, the eigenvalues they're supposed to be what? Big or small? Either big or small. It should be big or small.
Pretty big. I'd say big.
I think you're right. Yeah. So if big, then this level set will shrink, right? So something like that. If both of them big, you have this is a we have what we call this. I forgot. Was E? Yeah. This EUV will be, let's say EUV equal to 1, right? So we have a steep things here, right? And this is a EUV 1. This is that's I cannot. EUV 2. Okay. So PowerPoint's horrible. So maybe I just write one of these here. So if the value is big, then basically we will have like this will go inside there. So we have a kind of a steep paraboloid. So if this lambda is small, then we will push out and we'll get a more flat surface there. So then that's it. Basically, that's it. So here, as I mentioned here, so for this one, as an example, therefore we want the lambda. If it's a corner, we want both lambda to be big, and then if we have an edge, we will have like one of the lambda is big, the other one is small. If we have a flat surface, we have like both of them are small. So, and then that's basically the idea of Harris corner detector. It did make some tiny adjustment here. So basically, you want this region, right? This is the region that is both lambda. This is the lambda axis here, just try of lambda. So you want this both lambda to be big here, so somewhere here. So this edges. So the original paper used something to use some equation like this. So it's an equation more or less like this. So this is if different parameter alpha here, you have a function kind of like this. So if this C value is big, then it will be more or less in this region. Otherwise, it will be in the other region. So, and why he's picking this function is like, if you write it this way, this is really the determinant of the matrix, and this is really the trace of the matrix, in the sense that you can just get the, you don't need to really solve the eigenvalue problem there, so you can just pull out. So therefore, like this will be just if I have m equal to, as I said, this is just a determinant. Right? This is like A, B, C, C, and this is a trace. By the way, do you guys know what trace mean? What's trace of this matrix here? Remember? I think you may have like in one of the classes. So, okay. By the way, then determinant. Do you remember what's the determinant of this matrix here? So let's say determinant of this guy is, if I have a b minus c squared, yes. So it's like this multiplied by this minus this multiplied by this, and the trace is actually just the sum of the diagonal element. So therefore, like the trace is just equal to a plus b. So this guy is actually just equal to a plus b. So therefore, in a sense, you don't really need to solve the eigenvalue problem here. So you can just, from the matrix, you can get the values there. And then, as I already mentioned. So that's finally you have one refinement there is similar to what we talked about last time for edge detection. You can have some long maximum suppression. So because let's see if maybe I go to this one here first. If I just try to find the C values for each of the corners, you may have like very large patches here, like the large patches here. So then I would like to kind of like reduce the number of this response here, and so we can just say only when this is maximum, locally maximum, then we will keep that as corner. This can be very easy to verify. Right? We just like compare with the left, right, up, down pixels, and see if like it's smaller or bigger. If like all smaller than the current values, then we'll consider that as a true maximum. So this will be the kind of final result, something like this. There's a slight modification, like as long as the Shi corner detector is very much similar to like Harris corner detector, but it just use this instead. Probably the result is better, a little bit better, but then like you will need to solve lambda 1 and lambda 2. It's not that difficult. It's a 2D. You can actually write it down anyway. Yeah. So maybe just a kind of like a summary again. So we have the original image. So remember, we need to build the M matrix, right? The M matrix is like something like okay. We have the M matrix is something like some summation W x y, and you have this I x square I y square. This, how can I move this? And then I x I y and I x I y. So each of these is just like a high pass filter, right? So I can make this high pass filter, and then afterward, like, remember this is a if I look at this, I should move these windows around, right? But that's the great thing is that when I move the windows around, it's essentially the same as I doing a low pass filter over all these images here, right? So therefore, what we are supposed to do is like after we compute a gradient image like this one, then we just apply a low pass filter on the entire image, and then like you will have essentially 4 images here, or I should say like for each of the pixel, then we can build this M matrix here. So this is like essentially after the low pass filter here, and then like then as we mentioned earlier, we need to compute the corner length. It's just the determinant minus the alpha the trace, and that I can grab it from the value in the matrix there. Then we just pick a threshold to pick the high values, and then we will do the non-maximum suppression. So I have 15 minutes. So yes, any questions?
So R is your result. So why did it pick the center of the circle, and why does it pick the ends of the line segments? Is it just because there's a hole in the circle?
You mean here? There's a point in the circle, yeah.
Okay, so if it's a square or anything, then it's going to be...
Yeah, you think of like you move that, if you move the neighborhood patches, you've compared the current patches, like of the target pixel, if you compare with the neighboring patches, if it doesn't look the same, then it will be looks like a corner. Yeah. So as I said, like I'm thinking to make it the homework free. I guess you guys will finish that. So probably like oh, why I keep moving back to here. Okay, yeah, let's see if I have Well, actually, the title of that document is not right. It's kind of Harris. So let me maybe let me yeah, I need to have a camera right now because I occupying my Zoom is occupying my webcam in the laptop. So let's see if I can run it here. You can see something like that, right? Okay. This is what we have here. So it's trying to do this corner detection, and this is not the OpenCV implementation. I'm using my. This is your. You can implement that like pretty easily, as just I mentioned in just described earlier. So let me get out first. So as you can see here, so we should first change to kind of grayscale, right, from our BGR to grayscale. Then here I directly use a super filter. Let's see. Yeah, you can, yeah. This use a super filter for the gradient, but of course you can use something else. You can use DOG as we mentioned last time. It will be the same thing. So, but basically I will compute the X and Y direction gradient, right? And you remember the matrix, like the M matrix there, the upper left element is like IX squared, right? So here it's just computed IX squared there. And then I supposed to do a low pass there. So then here I just make a low pass filter myself. Or you can use the Gaussian blur in OpenCV, but I make up a low pass filter that I can control the kernel exactly, because if I do that. And the kernel here is like what we described last time. Let's see, where's the kernel here? Like, yeah, I make a kernel. It's like a Gaussian kernel with a PPF like from 0.01 to 0.99, and the size of that patch is like 9 by 9. So I just make 1D here and then outer product to form the patch, the Gaussian kernel there. Then make it a function, just make it easier to call. So, and then here, so therefore, like after I have X, I, Y here, I form for the matrix. I just get as I reset like A, B, C. The off diagonal is C there, and that I got it from doing the low pass filter with this IXX, IYY, and so on. Then okay, here is the choice here. I try both like Shitomashi and like Harris. For Shitomashi is trying to find the minimum of the eigenvalues, and actually you can find the closed form if you use a pen to just calculate that. Like you can find that value is actually something like this with this expression. Otherwise, if you use a Harris corner detector, you will have something like this. Yeah, this. Okay, I'm using Shitomashi earlier. Maybe this time let's try Harris. And then like for log maximum suppression, you just compare with the label, right? So I first build a mask here. Okay, maybe I can skip here just to show you if I don't have like long maximum suppression here. Let's see. So let's see. It's not too bad. Yeah, but I guess it's more clear now here that when I carve static here, without the long maximum suppression, I will be carve like this. Let's see if I turn on maximum suppression here. So you can see like that's basically like the become less much. The number of points like decrease significantly. Here, just for the sake of like visualization, I can't make the points a bit bigger because otherwise it's hard to see. So I just again use a filter to make each point size instead of like 1 by 1, like 3 by 3, so it looks like to be easier to see. Yeah. So so I guess that's it. Any questions? So I'm thinking to take this as the third assignment. But as you can see, again, I already show you the solution. So you just need to type it out. I don't really, yeah. So, but
could you explain,
Yeah.
I mean, maybe not since it's our assignment, but
Yeah.
how the non-maximum suppression works right there in
Yeah, actually, yeah, the long maximum suppression I did here, I try to make it vectorized. So what I did is you can think of like when I compare my current pixel with the next pixel, say there. Let's see. Oh, where's that? Where's my Suno again? So for example, like I suppose for each of the current pixel, I will compare with the next pixel, right? This one, whether it's like bigger than this, whether this one is like bigger than this one. So then what I can do is that when the comparison is the same as I doing a high pass filter, and then do a threshold, right? So if I do a high pass filter like of like 0, 1, minus 1, after the filter, if like this guy is bigger than this guy, then the value should be bigger than 0, right? Yeah, otherwise it will be like smaller than 0. So then this will be easier than, of course I can like exactly compare the pair. Then I don't need to consider boundary condition because if I use a filter.
and you just look at each neighbor to see.
Yeah, and then I only consider 4 labels there, so therefore will be 4 filters, and then I have a filter minus 1, 1, 0, and then I have a transpose of that. Of course, you can do more. For example, I can also compare these 4 corners here.
Sure.
Yeah, so, but I didn't do that. It seems sufficient. Yeah. So, any other questions? Hopefully not many people around, but hopefully the West won't complain about this assignment. What?
What you're using here, so if it detects an edge, it's not going to give you, just to be simplistic about this, you're not going to get a red dot, right? It's just an edge. So at some point, if you had, I don't know, a dodecahedron or something, maybe a 20-faced figure where the edges are, there is a corner, but they're really close to being straight. At what point how do you adjust that in what you've done with your algorithm?
Yeah, we'll talk about that next time, actually. That would be like, this is first, corner detector will be like, as you mentioned, will be kind of like scale related. For example, if you look at something, if you get closer, it used to be looks like corners, but if like close enough, maybe it's no longer look like the corners.
Right.
So then you need to be, hopefully we'll have like kind of like more resilient to like different scaling. So that's why people consider other feature detector. For example, sieve. The first one is sieve, basically the most popular, most famous one, and then later on they have like surf and so on, like several. So we'll talk more about that. But as homework assignment, I guess I'll just ask you to implement that, this one, so it's easy. And it's already useful, like for some application. Like for example, like you can use this for image stitching already. Like for image stitching, typically this is sufficient. Like you basically get the corners, most of the corners, and then the descriptor. We can describe more about the descriptor, but like you can use a rather simple descriptor, and then like that would be sufficient for you to do image stitching already. Yeah. Yeah. Okay. No questions? Then I guess we'll stop here.